Because incidence is such an important concept, I'm providing this second PowerPoint presentation in order to illustrate it from a more animated perspective. So let's think about the difference between a tour and a race. In a race, everybody starts at the same point, the gun goes off, and then you run, or in this case ski. We're going to have pictures of one of my favorite ski races, or drive, fly, or whatever mode of transportation or movement is being raced on that particular day, and you go from the start to the finish. And whoever gets to the finish fastest is the winner. However, when observing a cohort, such as a population over some generation or time period, not all will start at the same time, and not all will finish at the same time. In a tour, participants may enter or exit the tour anywhere along the route, and this is more like what we see in epidemiology. So our participants in this particular hypothetical situation will be 125 people starting on day 1, and we are going to observe them. So our original population is right up here, 125 on day 1, and they are all free of disease. But, as I suggested in our tour, there may be new members of the population coming in, such as immigrants or births, and these would be added in this column here. Likewise, we may have emigrants or deaths during the observation time. On this particular day 1, there was one person who either died or left the cohort. And then finally, we have to account for the new cases in our cohort, because once someone becomes a case, they are no longer at risk for the condition, and they must be eliminated from the original population at the next level, next time increment, in this case day 2. So as you can see, we lost one person to either death or immigration. One person converted from being free of disease to being a new case. Therefore, the population starting on day 2 that is at risk for disease is 123. Now, for this exercise, we are going to assume that immigrants or births and emigrants or deaths will be consistent or equally distributed over each day. That way, if somebody died at 12:01 a.m. and someone was born at 11:59 a.m., really they're not contributing a full day either way. But if we assume over the entire observation period that it all averages out in terms of coming and going during each day, we're going to be safe. And finally, I have a question for you, any English majors out there. Why is immigrant spelled with 2 M's and emigrant only spelled with 1? At least that's what the spell check did to me when I tried to put 2 M's on emigrants. Get back to me if you know the answer to that question. Our participants are ready. On your mark, get set. The gun goes off and there goes the racers. This here is the start of one of the annual Lake Placid Loppet events, which is most of these guys are heading right out for the double polling. Now this poor slob here is already tripped and fallen, and watch out because there's about 3 or 5 guys that are going to run right over him. So go. So we're starting with 125 people on day 1. No immigrations or births. 1 emigration and 1 new case. Starting with 123 on the next day, we get 1 birth or immigrant. No emigrations or deaths, no new cases. So starting on day 3, we have 124 that are free of disease and at risk of becoming a case. Day 3, no immigrants, and no new cases. Stays exactly the same for the next day, 124. We get 2 immigrants or births, 1 emigrant, 1 new case. Those cancel each other out effectively. We stay at 124. Not the same people, but the same number, etc. So what's this going to look like on a spreadsheet and on the tour. So to illustrate this, our tour starts on day 1 with one group, an entire population, in this case 125. Now during the first day, one person either dies or emigrates from the population, is no longer at risk for the disease, or is no longer at risk for becoming a case in this cohort, and there's one new case. And that's illustrated by these two arrows here. So here's the one person that contributed 1 day of person time and then emigrated from the cohort. Another person contributed 1 person day of time before they became a case. Then we get to day 2. We're starting with 123 because we lost those two. One person immigrated, so they did not start here. They're going to start right here at this arrow, right on day 2. And they're going to proceed along with the rest of the tour here. Now if you're wondering, well, how come the arrow only goes to here? That's because some people who join late may still convert as a case or die or emigrate early in the cohort compared to others in the orange that go all the way through. So now day 3, nothing happened. Day 4, lots happened. Even though it stays the same number, we have 2 immigrants. So it's shown by this arrow here, 1, and number 2, this one here. And then we had 1 immigrant and 1 who converted to a case. Those are signified by these 2 arrows. And then we've got day 5, no immigrants, but we have 3 immigrants and 3 new cases. So here, all those folks started at baseline, day 1, contributed 5 full days of person time, and then 3 of them dropped out, left the area, died, and 3 others converted to being a new case. And then finally on day 6, we had 1 additional immigrant, no immigrants and no new cases, and that's signified by this arrow here. And all of these are coming in or out of the cohort as the entire cohort, the other 113 people who started, is represented by this one big orange. So if you can imagine the crowd starting here and moving as the one orange arrow, and then these people starting, ending, new people coming in and ending or continuing. That's exactly what we're going to do with incidence. That's exactly how populations, which are dynamic, are happening in time. So if we go for 30 consecutive days, and we get these kinds of numbers of immigration or births, emigrations or deaths, and new cases, how do we calculate incidence out of this mess of people that are coming into the population, leaving the population? Some are converting to be cases, and others are just going to do the whole tour. Well, recall that your formula for incidence is, in the box here, the number of new cases divided by the population at risk per unit time. So the numerator is going to be easy. If we're going to look for incidence, say in this spreadsheet here, for simply days 1, 2, and 3, the number of new cases is simply the sum of these 3 here, which happens to be 1. The denominator can be a little more tricky. As I suggested, observing a population or a cohort is more like observing a tour rather than a race. So people are coming and going into the tour and leaving the tour throughout. So our denominator will actually equal the total sample size to start with, plus immigrants, plus births, minus emigrants, minus deaths. And then, for each day that we're observing, we must also subtract the new cases because they are no longer at risk for conversion. So let's look at row 1. If we were just to calculate the incidence at the end of day 1, we would have 125 in the original population, but we would lose 1 along the way, either through death or emigration, and 1 would convert to being a new case. Now, as you're first saying is, well, why don't you use 125 as the denominator? You could in this case. But over time, what we want, but over time, in order to assess this appropriately, and as I said, we are assuming that emigrants and immigrants and births and deaths are all going to be equally distributed over the 24-hour period. Therefore, we are going to take into account each one at each time. Otherwise, we'll get all discombobulated by the time we get down to the middle if we try to use 125 for the end of day 1. So our denominator for row 1 is actually going to be 125 minus 2 because we lost 1 person due to either death or emigration, and we are going to lose 1 as a converted case. So we actually are going to divide the number of new cases the number of new cases 1 by 123 times 1 day contributed per person. Then we go to day 2. If we were going to calculate the incidence from days 1 and 2 combined, we're going to start with 123 because that's how many we have free of disease in the population at the start of day 2. We're going to have to adjust for 1 birth or immigration, and in this day there were no immigrations and no new cases. Therefore, the denominator for calculating incidence at the end of row 2 will be 123 plus 1, which equals 124, times 2 days contributed per person, because we're now counting day 1 and day 2. So that leads to 248 person days that have been contributed thus far. So the denominator here is 124 persons times 2 days contributed per person. And likewise, row 3, we start with our population at risk, which is 124 from the end of the last row. On day 3, there were no immigrations or births, no emigrations or deaths, and no new cases. So the only thing that changed on day 3 was the number of days. So we're going to be summing the number of days here, so that now we're going to have our number of new cases, 1, divided by 124 people times 3 days contributed, or 372. So here is our average incidence from day 1 through whatever row we're looking at, and that will simply be this formula along each row, simply adjusted by the amount of person time contributed. And here's the whole shebang. So as you can see, the person time contributed will increase substantially. So incidence depends on the point of sampling. At time t1, for example, here, where this green line is, the average incidence may be 1 particular value, and at time t2, as some people have dropped, some people have converted, and some people have jumped in and contributed only small amounts of person time, you will have a slightly different incident rate as compared to t3 that averages over the entire observation period. And so now you're saying, well, so what, Dr. Hatch? What's the big deal about incidence? Well, let's see how it can be applied. If we look at the incidence of polio per 100,000 people per year, if we look at the initial clinical trials of the Salk vaccine for polio back in the late 50s, the incident rate measured in the vaccine group for paralytic polio was 16.5 per 100,000 per year, compared to the placebo group, which was 47 per 100,000 per year. Now we can see that that is a substantial difference and that the vaccine was highly effective. And here are the numbers for the non-paralytic polio incidence, about this very close, but with a population size that they had in the millions, that probably was a statistically significant difference. And then finally, fatal cases of polio. That's the power of incidence that can be measured over many years, even with thousands of people entering and thousands of people leaving clinical trial. Let's look at another one. The incidence of lung cancer per 100,000 person years in smokers and non-smokers in a 1995 to 2003 survey. Men who never smoked had an incidence rate of lung cancer, average incidence, 20.3 per person year, compared to men who smoked more than 2 packs a day as reported on the day of the survey. Their incidence rate for lung cancer was 12.59 per 100,000. I would say smoking more than 2 packs of cigarettes a day clearly puts you at high risk for developing lung cancer. And if we also control out for moderate smokers, 1/2 to 1 pack per day, we still have an incidence rate of 452 compared to 20.3. And of course you have similar results in the females. That's pretty powerful data. And that's why it is so important that we get our incidence rates right. To make sure we count the new cases out of the number at risk, not just the total population, but the number of people in the population that are at risk, and the time unit. It matters. Even if you're in a tour and not racing, it matters.